One of the earliest uses of neural networks in NLP was for n-gram language models. This paper by Bengio et al. From 2003 is not the first to do this, but it's the most well-known and the first to scale up to reasonably large datasets. In this video, we'll introduce neural networks by describing this model. Basic idea is to use a neural network to model an n-gram probability distribution. First, what is a neural network? We'll just think of a neural network as a continuous function with some learnable parameters. It has inputs and outputs, which are usually vectors, and it's usually a nonlinear function of its input. The term neural network has broadened in literature to refer to a variety of methods. I think it's better to think of neural modeling and deep learning as a modeling strategy, combining distributed representations, for example, vectors like word embeddings, and representation learning with nonlinear functions. For concreteness, we'll discuss a neural trigram language model. So, given the two previous words, we want to compute a probability distribution over possible next words x. The input to our network will be the concatenation of vectors for the previous two words, x prime and x double prime. We'll use this function emb that returns a d-dimensional vector or embedding for the given word. It's common to depict vectors using these rectangles with circles corresponding to vector entries. So in this visualization, the embedding for a word has 4 dimensions. We'll use this cat function to concatenate two vectors to give us our vector input to the neural network, which is C here. We'll assume the standard convention that vectors are column vectors, unless otherwise indicated, even though sometimes we draw them horizontally, as in this example. The output of our neural network is another vector, which we'll call S, and which will contain the probabilities of all possible next words. So its length is the size of the vocabulary. To get S from C, we do a matrix multiplication of a parameter matrix W and the input C. Then we do a softmax transformation, which we'll talk about in a minute. We depict this matrix multiplication visually in the neural network using lines that connect entries in C with entries in S. I'm only showing lines for the first entries in C and S for clarity. The lines capture the intuition that each entry of S is computed using all the entries in C due to the matrix multiplication. And each entry in C is used in computing every entry of S. This is often called a fully connected layer of a neural network, because there is a new vector being computed in which every entry of the new vector is computed using every entry of the input vector. We can also think of each line as corresponding to a single entry in the matrix W. If some entry in W is 0, say Wij, that's like breaking the connection between entry J in C and entry I in S, as that's how the matrix multiplication works out. Because it gets to be too many lines, we often simply draw a subset of the lines with ellipses to indicate a fully connected layer. What is softmax? It's a function that maps a vector of real values, called logits or scores, to a vector of probabilities, and it does so by exponentiating the scores and normalizing to get a distribution. This is written as a mapping from one vector to another. We can also write this in scalar notation, where we define a single probability pi as the exponentiation of the corresponding logit vi normalized by the sum over all dimensions. And equivalently, we sometimes just write it this way using the proportional to symbol. Okay, back to our model. What are the dimensionalities of each of these components? Well, if we assume the embedding function returns a vector in Rd, then C has dimension 2D. And since S has an entry for each word in the vocabulary, W is a matrix with dimensions vocabulary size times 2D. Then what are the parameters in this model? Well, the embedding function has D parameters for each word in the vocabulary, and then the W matrix has another 2D parameters for each word, so there are size of vocabulary times 3D parameters in total. Let's compare our trigram language model from before with our new neural version. The trigram model has a separate probability to estimate for every combination of the 3 words, the 2 in the context and the third to be predicted. We're going to think of those probabilities we got with maximum likelihood estimation as parameters to learn from data. So the number of parameters is the vocabulary size cubed. and it grows exponentially with n-gram size. However, most of these parameters are zero. Most trigrams are not observed even in very large corpora. And with certain smoothing methods like interpolation or backoff, most of the parameters still remain at zero. The neural trigram language model, on the other hand, only has 3D V parameters, where we have the option of choosing D, as it's just the length of the embeddings. Here, the number of parameters is linear in the n-gram size. However, no parameters are going to be zero unless we intentionally seek to make them zero, through some sort of regularization or something like that. And there's no explicit smoothing done here, though we can think of smoothing as occurring naturally through the use of distributed representations for words. So far, we've talked about a way to compute a trigram probability using a neural network with a single fully connected layer and a softmax. We'll collect together all of our parameters into W to match our notation from earlier in the course. But we haven't yet talked about learning. With n-gram models, we used MLE, which has a simple closed-form solution. However, with neural networks, MLE does not have a closed-form solution. Fortunately, we know how to handle this. Let's write down the quantity we want to optimize and use gradient-based optimization. Maximizing likelihood is equivalent to minimizing negative likelihood, which is equivalent to minimizing negative log likelihood. This gives us a new loss function, which is called log loss. Generally speaking, it's the negative log of the probability of the gold standard output conditioned on the inputs. The power of neural networks often comes from including one or more hidden layers in the network. Here we're including a vector h that is computed using a matrix multiplication of a new parameter matrix U and the input C. Then S is computed using h as its input. This vector is called hidden because it doesn't explicitly correspond to either the input or the output. It can have any dimensionality we choose and is viewed as a learned representation for the inputs. We introduced this as a matrix multiplication for simplicity, but to actually gain expressive power with this hidden layer, we need to include a nonlinear function. So we'll instead think of layer computation in this way, where we now have a parameter vector b called a bias vector that we add to the matrix multiplication, and then we have a function g that is applied element-wise to all entries in the vector uc plus b. The matrix multiplication plus a bias vector is also called an affine transformation, and g is referred to as the nonlinearity or activation function. Let's look at a couple of nonlinearities that are commonly used in practice. The hyperbolic tangent, or tanh, is convenient because it maps a real value x to a value y between -1 and 1. It's monotonic in its input, but squashes the output range from infinite to finite. The logistic sigmoid function has a similar shape, but outputs a value from 0 to 1, which makes it useful when we would like to interpret the output as a probability. There are many other widely used nonlinearities that are unbounded. This is the rectified linear unit, or ReLU, which is unbounded but only for positive values. And there are lots of variations that can work better than these in practice. Why do we use a nonlinear function for g? Well, consider this network with one hidden layer. If g is a linear function, then we can rewrite this as a single affine transformation, which is left as an exercise for the viewer. So, to benefit from multiple layers, we need some kind of nonlinearity. We briefly introduced neural networks and showed the functional architecture for the neural trigram model. We also mentioned training with log loss. There are many other questions that arise, like how do we efficiently do learning, what other kinds of layers are used in neural nets, how they relate to our classifier framework, and how do we choose the best architecture in practice. We'll talk about these in class and in future videos.